Hello everyone, this is Jiarong Xing from Rice University. In this talk, I will talk about how to mitigate adaptive link flooding attacks using programmable decentralized defense. Link flooding attacks are an enhanced version of traditional DDoS attacks. Instead of sending a large volume of traffic to victim servers directly, link flooding attackers create congestion on critical links in the network that carries most of the victim's traffic. To achieve the goal, link flooding attackers will first construct the network topology and identify some critical links. Second, they will find a set of public servers, also known as decode servers, that share the critical links with the victim target. Finally, the attacker floods the critical links by sending a large volume of traffic to decode servers. By doing this, link flooding attackers can remove an edge network from the internet without it perceiving any traffic. Link flooding attacks are difficult to detect and mitigate because the attacker can change their attack strategy dynamically. For instance, the attacker can attack different target links by sending traffic to different decode servers. They can use bottlenecks at different locations with different source IP addresses. And they can use different attack traffic patterns, such as heavy UDP flows or short-lived TCP flows or a mixture of them. All these strategies can help attacker evade the deployed defenses. Link flooding attacks happen in the network, so they require in-network defense. State-of-the-art defenses developed in the security community are based on open-flow SDN. At the heart of SDN solution is a central controller that works in feedback loops. The SDN solution can pull the link utilization or traffic samples to the central controller for further analysis. The central controller can run some algorithm to detect the attack, classify the traffic, and compute the defenses in the software. Finally, the controller will deploy the defenses to the SDN switches. Commonly used mitigations includes routing traffic to alternative paths or filtering suspicious traffic. Unfortunately, SDN solutions cannot handle fast adaptive attacks because of the following reasons. First, SDN controllers work in a feedback loop manner, which requires several RTTs to collect the data, compute defenses, and deploy them into the network. Second, software computation, like traffic engineering or integer linear programming, is very slow. On the other hand, adaptive adversaries can change their attack strategy very fast, which means they can evade the SDN defense. So in this work, we ask the following key research questions. Can we design a defense against a fast adaptive attack? We believe the answer is yes, and we build a repo in this work. That is the programmable decentralized link flooding defense against adaptive adversaries. Repo utilizes the recently proposed programmable switches, which can be programmed in high-level languages like P4. Programmable switches allow users to customize packet processing logic or network protocols without hardware upgrade. Once deployed into the network, programmable switches can run at line speed. The security community has used programmable switches to build a wide range of security defenses, but existing work mostly use them for single switch defenses. In this work, we will use programmable switches as the bedrock to build a decentralized link flooding defense. Our key idea is to decentralize the defense into programmable switches. By doing this, we can significantly tighten the feedback loop, and we can do packet inspection directly in the switch without sampling traffic to a central controller. Finally, our defense can operate at hardware speed, which is much faster than SDN controllers. As a result, repo can mitigate very fast adaptive attacks. However, decentralization brings unique challenges. In SDN solutions, the central controller provides a global view for the defense, but the repo is the distributed system in which switches only see local threat signals. We solve this problem by reconstructing panoramic views in a decentralized manner. Concretely, repo has a language for users to define the needed panoramic views for different attack defenses. Then we have a compiler that can compile the defense into switch local programs which can extract the local panoramic pieces. Finally, we have a distributed protocol that can reconstruct the complete panoramic view. So what's the panorama? Panorama defines the global thread signal needed for the defense. For example, the congested link in the network, the flow rate of some source IP addresses, and alternative paths toward to some destination. In repo, the panorama can be used in a key value semantic. For example, given a flow ID, the panorama can tell you the flow rate of it. Repo constructs the panorama in a decentralized manner. Different attacks require different panoramic views. Repo has a language for users to specify the needed panoramic views. This example shows how to use repo language to define the panoramic views for a core mail defense. Core mail is a specialized encoding attack in which the attacker uses heavy UDP flows or fixed TCP flows to enhance the attack effectiveness. In repo, panoramic variables are defined as recurrent values for some code snippets. The code body defines how to compute the panoramic variables. And the core logic for this defense is to use a reduce operator to aggregate the flow sizes and use a filter operator to identify heavy flows. Our next question is to extract the switch local fragments for the panorama. Repo has a compiler that can compile each operator in the defense into switch local P4 programs. But the repo compiler does more than that. The compiler will also perform automatic inference for the following information. First, the key for the panorama. Repo will remove unused keys. For instance, in principle, we should maintain all possible header fields of packets sent to the victim link. But the repo will find that only link ID is used, so it will only maintain information about link ID. Second, the repo compiler will infer the data structure and determine to use exact or approximate data structure automatically. For instance, it will find that source IP is the key for suspicious, and source IP is a very large space. So repo will use counting sketches to maintain suspicious. Finally, the compiler will also infer the access method. It will find that victim links is only used to test on its sizes. So the repo will only maintain the needed information to calculate the size. It will also find that the mitigation is never used in the following code. So mitigation is never constructed and synchronized across switches. Now each switch can extract the panoramic pieces. Our next question is to reconstruct the complete panoramic view. Our solution is to reconstruct the panoramic variables using some distributed protocols. Concretely, in the first step, each switch will extract the local fragment using the local switch P4 programs. Then they will exchange the fragments with their neighbors. And the neighbors will merge the fragment received from others. The protocol will run several runs, and the protocol can complete when all fragments are exchanged. At that point, all switches will have a complete panoramic view. There are more details in the paper. If you are interested, please read our paper. Next, I will show you the evaluation result of repo. We build a repo prototype and evaluate it in both packet level and flow level simulation. We use real-world topologies and mainstream link filing attacks proposed in previous work. We have built 3 SDN baselines. The first baseline is SDN sampling, which performs sampling, classification, and traffic engineering in the central controller. The second one is SDN routing, which only performs routing in the central controller blindly without traffic classification. The last baseline is SDN++, in which we give extra capability to SDN switches so that they can perform classification in the switch directly. Traffic engineering is still done in the central controller. In all cases, we use SOL, the state-of-the-art traffic engineering tools for SDN systems to perform traffic engineering. We first evaluate the effectiveness of repo in link flooding mitigation. Here we show the result of flow-level simulation for medium-sized topology. From left to right, we show the normalized throughput of repo compared to different SDN baselines. As we can see, SDN routing and SDN++ takes a longer time to mitigate the attack. SDN sampling fails to mitigate the attack. This is because the central controller can only sample a very small portion of traffic, which means they will miss most of the malicious traffic. but the report can always mitigate the attack instantly. Then we evaluate the effectiveness of report in adaptive attack mitigation. Here we show an adaptive attack with decreased rolling appears, which means from left to right, the attack is enhanced. We only show the result for SDN++ because it is the most powerful SDN baseline. We found that SDN++ gradually falls behind the attack, but the report can always mitigate the adaptive attack. We have more experimental results in our paper. Please read that for more details. Let me summarize the talk. We are motivated to mitigate adaptive link flooding attacks, and we found that SDN approaches works in a feedback loop manner, which are too slow to mitigate fast adaptive attacks. We build a report in this work, which is the programmable decentralized defense. Report has the language for users to define the needed panoramic views for different attack defenses, and it has a compiler that can automatically generate P4 programs to extract the switch local threat signals. Finally, it has a distributed protocol to reconstruct the panoramic view. Our experiment results show that report can mitigate adaptive link flooding attacks effectively and quickly. We have released the source code. Thank you for listening. I'm happy to take any questions.